400 million cubic meters. That is the volume of fill material dumped onto open water seabed mud sitting 20 to 30 meters deep, to manufacture land where none existed. Not soil, not bedrock. Mud. The kind of material that shifts under pressure the way wet concrete shifts before it sets. And on top of that mud, millions of tons of steel, glass, concrete, highways, residential towers, and living human beings. So here is the question every engineer on these projects eventually has to face, and that almost no public report ever answers directly. How does a city built on nothing not simply disappear into the seabed? 400 million cubic meters. The number lands before the mind has time to build a frame around it. To put it plainly, that is the volume of fill deliberately placed onto soft, water-saturated seabed sediment across some of the world's largest reclamation megaprojects. Sediment that, under any standard geotechnical loading calculation, should not be capable of supporting a structure of significant weight, let alone an entire city. The seabed in the South China Sea and the Persian Gulf is not rock. It is not compacted earth. It is silty clay, a material that, when subjected to sudden loading, behaves less like ground and more like a pressurized fluid. Engineers have a specific term for what happens when fine-grained saturated sediment receives a load it cannot redistribute fast enough. Liquefaction under poor water pressure buildup. The material stops acting like a solid, it flows. And yet the islands stand. The towers rise. People sleep in apartments, drive on elevated roads, and drink coffee on terraces that are, in the most literal geological sense, suspended above an abyss of soft mud. There is a real mechanism that makes this possible. It has been engineered with precision, and the full picture of how it works and what it costs has not been widely told. Before the mechanism can be understood, the weight must be felt. Consider the total fill mass of a single artificial island. The Palm Jumeirah in Dubai consumed roughly 94 million cubic meters of sand and rock. Its reclaimed footprint covers 560 hectares, comparable to nearly 1,000 American football fields placed side by side, but the Palm is not the largest. Forest City in Malaysia covers 1,386 hectares. The artificial islands of the Pearl River Delta, built for the Hong Kong-Zhuhai-Macau Bridge approach, swallowed dozens of square kilometers of shallow coastal sea. To make the mass tangible, the fill weight of a mid-scale reclamation project, 50 to 100 million cubic meters of saturated sand, equals the combined load of approximately 12,000 fully loaded Boeing 747 aircraft. Every one of them stacked and pressing downward, not onto bedrock, onto mud. Or consider this: 400 Empire State Buildings, each weighing roughly 365,000 metric tons, placed not on the granite of Manhattan, but on the silty floor of a shallow tropical sea. The seabed beneath these projects is not passive. Soft, silty clay in the South China Sea and the Persian Gulf typically holds a natural bearing capacity of 20 to 60 kilopascals, a measure of how much load per unit area the material can carry before it begins to deform and flow. Aggressive reclamation can exceed that threshold by a factor of 3 or 4 within the first months of fill placement. For scale, the Palm Jumeirah footprint is roughly half the size of Manhattan Island. The combined displacement of every active U.S. Navy aircraft carrier fleet adds up to approximately 2.5 million metric tons. The fill weight of a project the size of Forest City exceeds that figure several times over. So if the ground beneath cannot bear the load by any standard calculation, what force is actually holding it up? The answer begins with a concept that sounds deceptively simple: preloading. Before a single foundation pile is driven, before a single building column is poured, engineers deliberately place more fill weight onto the reclaimed land than the finished structures will ever apply. This excess load, called a surcharge, is left in place for months, sometimes years. Its purpose is not to build anything. Its purpose is to squeeze. In the Changi Airport Terminal 5 reclamation in Singapore, a surcharge of 4 to 6 meters of additional fill was applied across newly reclaimed zones and held for 18 to 24 months before construction began. That weight forced water out of the pore spaces in the soft sediment below, the same process that occurs when a saturated sponge is compressed, except the sponge is 30 meters deep and kilometers wide. But gravity-driven drainage from the surface has a fundamental limit. Pore water trapped deep in fine-grained sediment moves slowly, sometimes millimeters per year under natural conditions. Waiting for nature to consolidate a 30-meter clay layer could take decades. On a commercial timeline, that is unacceptable. This is where vertical drain columns enter. In the Pulau Tekong reclamation in Singapore, one of the most extensively documented artificial land projects in the world, engineers installed prefabricated plastic wick drains in a grid across the entire fill footprint. Each drain, approximately 100 millimeters in diameter, spaced 1.0 to 1.5 meters apart, driven down through the full depth of the compressible layer. The drains create a network of escape pathways, allowing pore water pressure to dissipate at rates that would otherwise take a generation to achieve naturally. The geotechnical paradox at the core of all land reclamation is this. Mud, correctly and patiently manipulated, becomes a rigid platform. The same material that behaves like pressurized fluid under sudden loading becomes, after controlled consolidation, a substance capable of supporting skyscrapers. The transformation is real. The science is documented, but it is neither instant nor uniform. Differential settlement is the consequence of that non-uniformity. A reclaimed island is never a single homogeneous block of sediment. Consolidation rates vary across the footprint. One zone may reach 90% of its final consolidation within 2 years. An adjacent zone may need 5. The result is measurable tilt. Millimeter-scale height differences between sections of the same island, the same building, the same road. In the Palm Jumeirah, independent interferometric satellite radar surveys, INSAR analysis conducted between 2010 and 2015, recorded vertical movement of up to 5 millimeters per year in certain zones. The island breathes, slowly, invisibly, but measurably. Engineers track this in real time using embedded piezometers, pressure sensors installed at depth inside the fill and the underlying sediment, transmitting pore water pressure data continuously. When pressure spikes, it signals that consolidation is incomplete. When pressure spikes unexpectedly, it signals something worse. So here's the question sitting behind all of this instrumentation, all of this monitoring, all of these carefully worded progress reports. If engineers can measure consolidation with millimeter precision from orbit, why do official project reports consistently cite subsidence figures significantly lower than what independent satellite measurements record? But here is what the official reports do not show. Forest City, Johor, Malaysia. A 1,386-hectare artificial island built on soft estuarine mud at the southern tip of the Malay Peninsula, one of the largest single reclamation projects in Southeast Asia. In 2021, an independent INSAR analysis using satellite radar interferometry at millimeter scale resolution measured subsidence of 25 to 30 millimeters per year across several active construction zones inside the Forest City footprint. The developer reported figures for the same zones, under 10 millimeters per year. The gap is not a rounding error. It is not a difference in measurement methodology. It is a factor of 3. In the Pearl River Delta, the coastal zone of Guangdong Province, China, home to some of the most aggressive coastal reclamation on the planet, multiple space geodesy studies published between 2015 and 2020 recorded subsidence exceeding 30 millimeters per year in reclaimed zones. In several documented cases, differential settlement between adjacent building clusters produced stress fractures in connecting infrastructure, not visible from the street, not announced in any press release. Here is the important clarification, and it matters. Accelerated subsidence is not by itself a sign of catastrophic failure. In the language of geotechnical engineering, it is an accepted outcome. The sediment is consolidating. The island is finding its equilibrium. Engineers design for settlement. Foundations are pre-stressed. Utility connections are built with flexible joints. The system anticipates movement. The question is not whether the ground is moving. The question is whether the rate will stabilize before the critical threshold, the point at which differential settlement begins to compromise structural integrity, is crossed. And that question is not answered in any publicly available documentation for Forest City, or for the Pearl River Delta reclamation zones, or for the majority of artificial island megaprojects currently inhabited by real people. The gap between public reporting and satellite-measured reality is not an accident. It is a structural feature of how mega project risk is communicated to investors, to residents, and to the governments that approve the permits. The engineering is real, the science is documented, the cities are standing. People wake up every morning in apartments on these islands. They make breakfast. They take their children to schools built on reclaimed land. They go to work in office towers whose foundations are anchored in sediment that 30 years ago was open sea floor. The islands hold. The towers do not fall, and the ground beneath them is still moving, slowly, measurably, in some zones faster than the official figures suggest. At what point does monitored, accepted, expected subsidence become something that can no longer be managed? At what point does the rate of movement outpace the capacity of the infrastructure to absorb it? At what point does a city built on engineered mud cross the boundary between controlled settlement and something that has no controlled resolution? If the ground beneath an entire city is slowly moving, at what point does it become too late to stop? The forces operating beneath these artificial islands are not unique to them. The same geotechnical processes, poor water pressure, differential consolidation, long-term subsidence, are active beneath other megastructures this channel has not yet examined. Structures that are older, larger, built before the era of satellite monitoring. The numbers there are different. The mechanisms are the same.